Okay, good morning. It's my pleasure today to introduce Päivi Törmä, who is a member of the Scientific Advisory Council of IFIMAX. We're especially happy to have her visiting. Päivi did her PhD in the University of Helsinki on actually theoretical quantum optics. Then she did a postdoc in Ulm University first, and then in Innsbruck with Peter Zoller, working actually on the theory of ultra-cold Fermi gases, one of the first theorists working on that. And then moved to Jyväskylä as a professor in the north of Finland, where she started actually doing experiments. So she's one of the brave ones who did the step from theory to experiment, and has been doing experiments on nanoplasmonics, photonics, and so on, and still keeping going kind of program both in theory and experiment, and actually then moved in 2008 to Aalto University, which then was still called Helsinki University of Technology, and has been kind of one of the pioneers of using plasmonic systems, looking at Bose-Einstein condensation, superconductivity, which is, you will see a very broad program here. She has also received quite a few awards. I think the one that sounds nicest to me is the first, how is it, the Order of the White Rose of Finland.
Yeah, I'm a knight.
Yes. So be careful if you have aggressive questions, he's a trained knight. And with that, it's my pleasure to give the floor to Päivi. And thank you for coming. And we're looking forward
Thank you, Johannes, for the kind introduction. And thank you for inviting me here. It's really a pleasure. This is my first visit to your university, although I have been to Madrid before. So I will start by telling about my favorite factor of two problem that annoys me. You know, you often encounter this factor of two problems, but I have a special one. And then I go to quantum geometry. First, from the theory point of view, I tell how it affects superconductivity and Bose-Einstein condensation. And don't worry, I will also explain what quantum geometry is if you don't know by now. And then I go to my experimental activity, where we also are obsessed with this quantum geometry. And finally, I go to systems which don't have quantum geometry in this sense, because they are not even periodic, namely quasicrystals. So let's start with the factor of two problem. So you all know how wonderful superconductivity is. Things can levitate, and there are a lot of applications. You can make large magnets, you can do quantum computing, you could also do classical computing with superconductors. This has been demonstrated, and have levitating trains and so on. And also in fusion reactors, one makes one use of big magnetic fields which need superconductors. So this one actually is a new high TC superconductor magnet of a fusion startup. So all this, of course, would be much more widespread and influential to our society and help us to reduce our energy consumption radically if we didn't have this factor of two problem, that the TC is still just 150 Kelvin, not 300. And it's funny, when usually for physicists factor 2 is not a problem. You just go to the lab or your computer, you work 1 year and that's it. So what's so difficult here? Well, let's remind us the basics of superconductivity, that electrons make Cooper pairs, spin up and spin down usually. And then the interaction that makes them to pair is usually very weak. And one can do then BCS theory and show that the critical temperature is exponentially suppressed. So U is the interaction, and the other stuff here, this N0 is the density of states. And this comes because there is a large competition between the interaction and kinetic energy. The electrons want to move, they don't want to pair. And that leads to the low critical temperature. And when you see that something is exponential, then even a factor of 2 might be a problem. Now, the obvious cure here is that, okay, let's remove the competition with the kinetic energy. So basically on other side, you can say the same thing by saying that let's increase the density of states. Of course, you can also increase the interactions, but that's maybe more difficult. So what can we do in terms of increasing the density of states, this N0? So let's do it by completely removing the kinetic energy. And then the interactions should dominate. And this you can do by so-called flat bands. So here we see an example of a very, very simple band structure in a periodic system, like here. And this is the famous Bloch function. And by the way, we will be very much interested in the periodic part of the Bloch function here. Now, in a flat band, the interaction is just bigger than the bandwidth. So the band doesn't need to have like zero bandwidth, but small. And then, of course, your group velocity is zero because energy is constant. You have no dispersion. So if you do now the simple BCS theory in this band structure, you will see that critical temperature is linearly proportional to the interaction. And you can see in the other case, it was exponentially suppressed. So this can be a dramatic improvement. And this V is a volume of the flat band. So that sounds wonderful. However, here this TC is just given by basically the absolute value of the pairing gap. So when superconductors are formed, there is an order parameter, and the absolute value of the order parameter is the measurable quantity. It's the gap for single particle excitations. But the order parameter, of course, is a bigger thing, and just having the gap is not enough. This is because to really prove that you have a superconductor, you have to show Meissner effect, dissipation-less current, and so on, supercurrent. And supercurrent is very different from usual current. The fundamental equation is different. So for usual current, you could maybe, this is conductivity, have infinite conductivity, but it's not the super conductor. You have to have this relation, current equals vector potential and a thing called superfluid weight. And of course, then this has to be finite. So you see the vector potential, maybe remember that, oh, it's not gauge invariant. So what does it mean? So that equation actually is in the London gauge. There is also another thing that is not gauge invariant. It's the phase of the order parameter here with the general R position dependent phase. And then the combination of phase gradient and the vector potential is gauge invariant. So the vector potential is related to change of the phase of the order parameter. So this allows us now to relate this superfluid weight ds to the free energy change that you have when you have a change in the order parameter phase. And this basically means that the Cooper pairs are moving. So the ds is like the inverse mass of Cooper pairs. How heavy are they? Can they move? Good. And it's also related to the London penetration depth if you want. So we should have obviously finite superfluid weight to be able to have finite supercurrent. And let's see, the BCS theory gives, let's just focus on the first term here. This one, this other one is small. So here you have a particle density or Cooper pair density divided by effective mass, which in the flat band, unfortunately, this term is zero because the mass is infinite. So now it seems like, okay, you get easily Cooper pairs, but do they actually move? Because it looks like that superfluid weight is zero. Fortunately, this is not the end of the story because the flat bands that we are actually interested are quite curious. I mean, you could have a flat band just by binding your electrons like really tightly on the individual atoms. This is the atomic limit. Nothing absolutely doesn't move. But that's boring and uninteresting. The interesting flat bands are like this. their localization and flat bands are formed by interference. So nice example is the Lieb lattice, where you can have wave functions that have minus amplitude here and plus here, and also minus here, plus here. Now, if there is some tunneling process, these will kill each other. They will destructively interfere, and therefore you get a flat band in the spectrum. So in this kind of multi-orbital unit cells, you can have destructive interference and you create a flat band. The same happens if you have a superlattice, and for instance, Moir materials are like this. There you start folding and you make your bands flatter and flatter. These are actually the same thing, but in different limits, so to speak. And Landau levels are also interesting flat bands. So we then set a program to see how does the superfluid weight actually behave in this kind of interesting flat bands. And the key is that you have to take it as a multiband problem. You have to understand that there are many atoms, many orbitals. And here I would like to highlight my co-workers, especially from my group, Sebastiano Peotta, with whom we started this, and Kukka Huhtinen and Long Lian were very important. And collaborating groups like Sebastian Huber and Andrei Bernevik and their groups have been also very important. And this is not the full list of papers, but it's the early ones. So BCS theory in the multiband system, you could start by doing something like this. So this is a famous Hubbard Hamiltonian. This describes hopping of electrons, interactions on site, and so on. The point here is now the alphas and betas, which refer to the orbitals inside the unit cell. Like in the Lieb lattice, you had 3, so this index would run out over that. And we have assumed some kind of attractive interactions that could come from electron phonon or something else. And then we calculate the superfluid weight. So this can be done by introducing period, not period, but some spatially dependent change of your order parameter phase, and this is the Cooper-Pell momentum, and then seeing how it affects the free energy. Alternative thing is, and you can understand why it is equivalent because of this this relation being gauge invariant. You can just look at the linear response to the vector potential. So with these things, okay, this is details. Yeah, you can replace F with omega. This is the main result. We found out that the superfluid weight has 2 parts. The first one is proportional to the dispersion derivative, meaning to the inverse of the effective mass. And this is known, and this is what everybody has looked. But there is another contribution that only exists in multiband systems, and it can be non-zero in a flat band. We call it geometric, and you will soon see why. And now we have to come to this, what is this quantum geometry about? So I introduced the basic concept of quantum geometry called quantum geometric tensor. And it was introduced initially because these people were interested in defining a metric for the distance between 2 quantum states. So here you see a formulation of the infinitesimal distance between 2 quantum states when you change some parameter, say k. In our case, this k is usually the lattice momentum of periodic system. And then if you introduce a gauge invariant version of the metric, you come up with actually a more general tensor, which contains derivatives of your wave functions and some projectors and so on. And the real part of that is really a metric for the distance, and the imaginary part is curvature. And you know, integrating that over the Brillouin zone, you get the chair number. So quantum geometry, somehow it also includes topology, but it's a broader concept. It tells also of other types of properties of the wave functions. And I always say, this is what I recommend to young people, that if you encounter something new and want to understand it, reduce it to an example that is almost trivial then it's easier to grasp it. So here, let's take a Hilbert space which has just two states, the two-level system, 0, 1. And one can parameterize it completely with two angles, and you can pictorize it in a Bloch sphere. Now, taking these equations, you can now easily calculate the quantum metric for the angles phi and theta, and also mix theta, phi, and so on. And for instance, for phi, it becomes sine theta squared. So now, look, if you are at the North Pole, then if you change this phi here, it doesn't actually change the state at all, because a phase in front of quantum state is trivial. So therefore, your quantum metric is 0. But then in the equator, quantum metric is finite, and indeed, if you then change phi, you change the phase here, and that can make your new state a little bit orthogonal or completely orthogonal. So it's a state tells how much you actually change the state when you change some parameter, and this can vary very non-trivially in your Hilbert space. Okay, so we call it geometric because we can show, basically it comes from interband term, so that's quantum geometry to start with, but we can show that in certain limits the superfluid weight becomes directly proportional to the interaction and the quantum metric. That's quite nice. And to look a little bit more details of this limit. So the limit is when we are in flat band, interaction is bigger than the bandwidth, but the interaction is smaller than the band gap to the next band. And then we also assume that it's very homogeneous. Then this is the final result. So here superfluid weight has proportional to the interaction to filling. Nu is filling, number of orbitals, and this thing is the quantum metric integrated over the Brillouin zone, and also it's important to take the so-called minimal version of that. So then you can also, in this limit, connect the gap and the filling, and this then tells you that superfluid weight is proportional to the square of the gap. So this proportionality is completely different from the dispersive case, where you had the number of electrons divided by the effective mass. So this could provide you superconductivity in a flat band. And furthermore, it's nice that this quantum geometric tensor is positive semi-definite, so you can relate the real and imaginary part and derive this kind of lower bound for superconductivity. So whenever your band is topological, you can have superconductivity. Of course, you have to check also whether there is competition with some other phase, like charge density waves, ferromagnetism, and so on, but at least the band allows transport. So now we have come one step forward in this factor of 2 problem, because I mentioned that to search for high critical temperatures and nice superconductors, you could vary interactions, you could tune the density of states, but this shows that also the Bloch functions, namely quantum geometry, is very important. So you could use that in your search of better superconductors. Good. So how to understand this kind of intuitively? My first thought, once we got these results, is that, okay, let's redo the Cooper problem. So Leon Cooper just solved the two-particle, two-body problem, which is like all of you have done it as a quantum mechanics exercise. But assuming the scattering is limited by Fermi C. And quite amazingly, he got the same TC up to factors of 2 and so on than you get from the mean field many-body prediction. So could we do the same for flat band? So we did it, but it's not at all the same approach. Here is just a Schrödinger equation for 2 particles, kinetic, some potential, and you solve this, and this is very easy to solve, at least numerically. But in the original Cooper problem, you put the restriction coming from the Fermi sea. Now, if you have a flat band, you don't have a Fermi sea because all energies are degenerate. So what can you do? Well, the question there is more like that, okay, in the flat band, in non-interacting system, everything is degenerate, nothing moves. So if we introduce interactions just for between the two particles, does it break the degeneracy? Does the pair get a finite effective mass? Like single electrons have infinite electron mass. What about the pairs? And we did the calculation. Here is the binding energy. V is just telling how the different orbitals are interacting. Lambda is the interaction. So you immediately get the bound state, and it depends on Q, which is now the center of mass momentum of the pair. And you can expand it to see, in some limits again, to see that the inverse effective mass of the pair is given by the quantum metric. So this is the same thing that we got from the superfluid weight, because that's also like inverse effective mass. So it's quite nice that again, also here, the two-body problem gives you the same result as the many-body problem. And this also allows you to maybe get some intuition that, okay, single particles don't move, but then a pair is able to hop. And that's given by quantum geometry. And here a bit more intuition why quantum geometry then is important. Well, here you can think about a trivial type of flat band where electrons are just bound to the atoms and there is no overlap between the wave functions. So then if you introduce interactions, you get some kind of on-site pairs and nothing much happens. But then you could have these interesting flat bands where the flatness comes from interference, and there your wave functions, namely one-near functions, they can also overlap. And then in the interacting system, this overlaps allows the pairs to move. And this is related to quantum geometry because it's very well known that, for instance, topological properties control the localization of wave functions, one-near functions. Also quantum metric controls them. So this makes it understandable that we have this Chern number bound, which just cannot localize the wave functions if it's topological or has non-trivial quantum geometry. All right, so all of you probably have heard about twisted bilayer graphene, where they do have flat bands. Here, this is calculated band structure, very flat bands there. So is this relevant? Well, people have been looking at it. I mean, it's still very open whether it's truly relevant, but there are two very interesting experiments now where in one of them, this one, they deduced the superfluid weight somehow indirectly, and in the other one, they actually measured it. And as a function of filling, it's this kind of dome. And if you look at what the single band PCS theory predicts, is these kind of lines which obviously don't fit at all. While if they kind of scale with the gap somehow, it matches better, and that's what our theory suggests, that it should more follow the gap. So this is a nice indication that maybe these things actually play a role. But one would need much more precise experiment theory comparison to really prove it. Good. And then my group has progressed also beyond usual supercurrent, because supercurrent actually in superconductor is an equilibrium property. But you can do many things with your superconducting samples. You can, for instance, put a voltage difference across it, and that's the non-equilibrium. I will not go to the details of this, but just to tell that what we found is that the Cooper pairs in a flat band, they can go through, but quasi-particles, which are always there, like thermal or whatever, they don't propagate, at least in this study. So this could be nice. Maybe it helps to have system free of quasiparticles. So the point here is that not only quantum geometry and flat band superconductors can be better for critical temperature, but they could offer new types of superconductors. All right, so that was about superconductivity, and then I want to go to Bose-Einstein condensation of, let's say, atoms or polaritons, or what is your favorite boson, and see whether quantum geometry plays a role there. So here we have basic equations about the weakly interacting Bose gas. Now in free space it has some effective mass and parabolic dispersion, and one can easily calculate what is the quantum depletion, so the amount of particles that are in the excited states due to interaction. So U is here a small repulsive interaction, and N0 is the density. Fine, this is well known. So then let's go to the flat band limit where effective mass is infinite. You can easily say that your excitations kind of seem to explode. And this is understandable because no energy is now lower than others. So if you try to condense somewhere, you can easily, any interaction will put you to any other state because they have no energy cost. However, again, this is some kind of simplistic single band picture, and if you really look at the multiband system, there were some works that showed that, okay, you can still have Bose-Einstein condensation. But we wanted to understand what exactly determines the stability of some condensate, and of course at that point we already had a hint at or idea that it might be quantum geometry. And this is really what it turned out to be. So here, I mean, the example shows the Kagome lattice where you can have a flat band either on the bottom or on the top or bottom, and then the condensation could happen in a dispersive system or in a flat band. But our results, they are more generic than just this model that I wanted to have some illustration. And what we found is that in a flat band system, the speed of sound becomes proportional to the interaction, U, and the density, N0, and the square root of the quantum metric. So again, quantum geometry gives you stability of the condensate because of course it has to have a finite speed of sound, and also the interaction dependence is different. So this, that everything is linearly proportional to the interaction, is a typical flat band feature because there is no other energy scale, so everything should be like that. And then we looked explicitly at its excitation fraction NE here, and found that that's proportional in low interactions just to the quantum distance between two states. So here Q is the Kc is the condensation momentum, and Q is the momentum of the other state where the excitation, you are trying to create an excitation, and simply the distance between the quantum states kind of prevents the condensate to go to all possible states. So that's really interesting. Now the distance comes and not the quantum metric, and this is because this is not a low energy property, it's really like going to the excited state. And this means, this relation, that if you lower the interactions, the amount of excitation compared to the total number of particles, that stays finite. So this is an ideal system of looking at beyond mean field effects, because in a BC these excitations are the beyond mean field. So that's very much along the line of thinking that flat bands give you access to non-mean field physics. All right, so that was all about the theory, like theory only, but I now go to explain these results where we do both experiment and theory in my group. And this one is related to this quantum geometric tensor, but now in a photonic system, in a plasmonic lattice. And here, the first order is from here, from this university, Javier Coerra. So maybe many of you, or some of you, know him. And Jani was then doing the experiment. Javier did the theory. Now I have to, yeah. So when this quantum metric became popular, people started to think that they might want to measure the whole quantum geometric tensor. I mean, Berry curvature has been measured like millions of times, but what about quantum metric? And the first systems where it was measured are shown here, either optical or some artificial quantum systems. Now there are very new papers that it's also done in solid state physics, but it's much more difficult there. Anyway, this was the starting point. So then our observation is still like one of the first ones. And now I need to tell a little bit what kind of systems do we look at. So they are a plasmonic nanoparticle array. So in the same image you have like, oops, right? Yeah, like nanoparticles made of gold or silver or something like this. And they have plasmonic resonances, so they are individually like small antennas, but of course if they are arranged like wavelength apart, you will get collective modes due to interference of the radiation. And these collective modes are called surface lattice resonances. And they are very dispersive and very, let's say, polarization dependent, because you can think that with driving with this polarization you create radiation in this direction and so on. So we get two TE and TM modes typically in a simple square lattice. They are depicted here, and if you calculate in empty lattice approximation the whole thing, it can look like this. These are different diffracted orders, basically, of the lattice. Now, when we go for the quantum geometric tensor, I told that it's a multiband thing. So in this problem, two bands are not like any of these two bands here. I mean, we look at actually only a one band. I think it was actually this one. Eek. Doesn't matter. Something like this. But that has two polarization directions. So the two polarization directions are now the two bands. And those can be easily mapped or parametrized and connected to the Stokes parameters. And to get these quantum geometric properties, one really needs to know the wave functions. In this one, both the theta parameter and the phi. It's not completely straightforward to get both of them, but there is a nice method. It's kind of tomographic, I would say, that you have to measure all energies and all momenta of your system, and at each point with six different polarizations. So this allows you to map the Stokes vector completely, and from there you get the phase. And then you can calculate the quantum geometric tensor, but that one involves derivatives of the flow function. So it's actually numerically very, very tricky. You try to get something from experiments that then you can take derivatives. So here I really highlight the contribution of Javier actually managing that. But it also required a brilliant experimentalist, as Jani, to get clean enough data. But in principle, it's simple. So let's go to the results. So here are some snapshots of basically just transmission along the diagonal of the K-space. And then we extract from that kind of measurements the quantum metric and the Berry curvature. And you see, first of all, that they are non-zero. And they are non-zero along the diagonals. In typical tight binding systems, you get Berry curvature around the band touching points. But here you get them on the diagonals, because this is a radiatively very long range coupled system. But why on earth we get quantum metric or even Berry curvature from such a simple, almost trivial system? So we understood this by constructing a two-band model for the two polarizations. And since this can be simulated very well with T-matrix calculation, we could validate our two-band model, two model very well. And it looks like this. We introduce some couplings there. They are momentum dependent and so on. And from that, we can analytically calculate the quantum metric and Berry curvature, and they look very, very similar as our experiments, like this. And then we can play with the different parameters of the model to see when do we get the result that gives the experiment. And we found out, of course, for quantum metric, this coupling has to be non-zero. So we have pseudo spin orbit coupling in this system. And this is funny where it comes from. It's different from, for instance, from polariton systems. So here, if you look at some momentum k, meaning that the light field is traveling this way, and then the two polarization, they create very different kind of near fields. And you see these two are not 90 degree symmetry connected. So it comes from the fact that these are really nanoparticles which create some kind of non-trivial near fields or radiation directions around them. So this gives the quantum metric. And for the Berry curvature, we needed to introduce losses in the system by having this imaginer. So there is, of course, nothing, no magnetic field that would break the time reversal symmetry, but there are losses, and that breaks it. So it's actually the first observation of this non-Hermitian Berry curvature that has been proposed. Okay, so now I want to give the big picture of quantum geometry, a bit the history too. That these concepts were first thought about in the 90s already in some topology things, but mostly in the effort of Marchari and Vanderbilt to create optimal one-year functions for DFT. So that's where it comes. Then it went to quantum information. And then around 2013 and 15, let's say this one, our work is circulated with red, and these, they kind of showed that it could have, this quantum metric could have broader influence on condensed matter physics. And then it kind of exploded. You see, there are a lot of things, many things actually missing also, like nonlinear optical responses. There it's also important. And below you can see some review articles. If you get interested in this, you can find all of them on my Google Scholar. Good. So I have like 5 minutes for the last topic. So all this was related to the properties of the Bloch function. In the examples that I consider, the Bloch functions come from periodicity and so on. So we have to now forget about this because I go to quasicrystal, we don't have any periodicity. But there is topology there as well, in a bit different meaning. And here again, now the brilliant experimentalist is the same, Jani Taskinen, and then there are, and Rebecca helped a bit in the end of this, and then brilliant theorist Christian Arias and Grazia Salerno on this paper. And this relates to the very fashionable topic of bound states in continuum in photonics. So these are states that energetically in the continuum but are not coupled to it. And in photonics, this can mean that they are bound to, let's say, your optical structure and don't radiate, even if the energy is in radiative continuum. And they can have very high Q factors, which is nice. And then you can design a little bit of imperfection that some light comes out, that they are useful. But they are very interesting in the sense that you can understand them as vortices, and the topological charge is the winding. So if you look at how how the polarization may wind around a point in K-space where you have your BIC. It could be trivial, or then some 1 or 2 windings of the polarization, and the direction gives you the sign. And this is the definition. It's really just the phase of the polarization. And of course, because the polarization is winding, it's not defined in the center. And this means that in far field you cannot have radiation there. So this makes these modes dark. And yeah, these are the many applications that you can have. So then experimentally, these are quite straightforward to identify, because here I have drawn with black the polarization direction, and then if you put a polarization filter to your output and rotate it, then you will see some parts bright and others not. So there are like 2 blobs rotating with your polarization filter, and the direction gives you the sign, and the number of blobs gives you the charge, the topological charge. And there is a group theoretical approach for designing how many charges, which symmetry you need to get a certain charge. So in our paper we have this formula, and you can see immediately here that, okay, in any periodic system I can go only up to charge 2. Because in 2 dimension, if you want to have some other symmetric groups, you must have a quasicrystal. So we wanted higher charges, we went to quasicrystals. And then, there are all, if you want certain charge, you need to kind of address one irrep. There are always many modes, increasingly many modes around some, let's say, gamma point and so on for high symmetries. How do I get my favorite irrep? So our approach is like this, that let's take in a computer the approach where we have waves which kind of follow the symmetry, but with the phase shift that corresponds to the irrep. And we let them interfere and make a pattern. And then we put the nanoparticles to the nodes of that pattern, because for that particular irrep then there is less losses. So that should start lacing. So this is like forcing a particular irrep to lace. So sounds simple. It was in practice not simple at all. We made many tricks, but in the end it worked. And this is just 3% of some kind of sample. So you need to have a computerized code to doing this. Just not like that. Maybe the very beginning in the center you imagine, but not the rest. And this kind of mess then. Yeah, see, I don't have the title because when I showed this to a student who was not involved in the process, she said, and this is the simulation. No, this is actually the measurement. So this is a K-space image. So this is angle, but it's the same as the K vector. And this is 12-fold symmetric. So everything is nicely 12-fold, very complex, but all the way here you can see features that are really symmetric. And when we zoom in here, we can see a lot of features. And with the polarization filter, something is winding, but this is much more complicated than we could imagine. So we started to analyze. And first of all, the fact that there are these blobs already without filter, this means that there must be 2 charges nearby. So that creates this kind of little blobs. Like here it's 5 and, oops, what did I do? Sorry. Yeah. Yeah, and then if we put the polarizer, we see this kind of thing coming. And that is actually there even in the experiment. You see here, this feature here is this kind of thing that comes when you have 2 charges nearby and a certain polarizer. So we have 5 and 7 there, and then we can look, and these blue ones are some simulations, and the lower one is also simulation, and there we see how the charge changes when we go radially, so that in the where is it? This outer ring, actually it's a combination of minus 17 and plus 19. So this 19 is really really high topological charge. I think highest that has been created in lasing. So this is all lasing. It's also all coherent and so on. Laser light with this kind of polarization winding. Then this should now go away. Is it this? No. Yeah, here, height floating. Yeah. So in some conference, somebody asked me that why are there so many primes? And that's interesting. Oh, okay, there you see the formula that gives us the charges. So you can get any, because this M can be any indicator. So there are like infinitely many of them. And no, what's... Did it get blocked now? Oh. All right. Yes. So I can massage this a little bit, so that for 12, for instance, we get the charges are 1 plus 6 times some integer. And now there is this Dirichlet's theorem that for any co-primes, A and D, there are infinitely many primes of the form. So now in our case, this A is 1, so it's co-prime with basically with anything. So we will have a lot of primes, and actually this series, it contains, at least in the beginning, mostly primes. I mean, there are also some non-primes, but yeah, so there is some kind of connection here. I mean, everything in the physics is just symmetry, and I actually think that we should start physics teaching from Noether's theorem and group theory, but people usually don't believe me. Good. So furthermore, when we look at the lasing in the K-space, it's flat band. And it's funny because the dispersions simulated and measured without lasing, I mean, there is some kind of quasi-period there, even when it's not periodic. So why do we get this flat band lasing? So that's because quasicrystals, actually, they have a continuum of Bragg peaks. They are just exponentially weaker and weaker. So here you see how if we amplify our dispersions, we get these peaks visible. So somehow the lasing seems to utilize all of them. And now I'm already a bit over time, so I just summarize that quantum geometry is important in superconductivity and BC, and we have and also in photonics, and we have this quasicrystals now, and I would like to solve my factor of 2 problem. Okay, thank you.
Thanks for the very nice talk. We have time for questions.
So thanks for the nice talk. One question regarding the superfluid weight. Mm-hmm. How important is it that the flat band is isolated? What does it happen if the interaction is larger than the gap?
Yeah, so the isolation is important only for obtaining nice analytical results. So if it's not isolated, we have checked numerically that the story is pretty much the same. You will get the current and so on. And in some cases, like a Lieb lattice where you have flat band and something touching it, actually it's very good. The superfluid weight grows not only like U, but even with a higher exponent, so like logarithm or something. So it's no problem at all, but except for the theorist who wants to have nice analytical results.
Yeah, I have a similar question. Normally, the superfluid weight and the Drude weight are connected.
Yeah.
And the Drude weight is really a Fermi surface property. Now, you're saying that you are having interband transitions. So I'm not really getting, so this connection does not hold in your case then?
Yeah, so the Drude weight and superfluid weight are actually the same thing in a gapped system. So if you would have something that is gapped, then they would be the same. Then of course,
well, in the super conducting state, it is gapped. So this is why
they are the same. But then of course, if you want to compare to metals, somehow the connection goes away because they are not the same thing anymore. Because you can have a Drude weight in a metal and it's not gap, and so that doesn't have then something to do with the. So, but I mean the interband terms are always there.
Not for the Drude weight. That's what I'm meaning. The Drude weight is a truly intraband property, Fermi surface property. And normally you make this connection just because you have this change of limits, and you can do this because of the gap.
Yeah.
And so I'm really wondering why this analogy is not working in your case, because you are having these interband transitions which are actually absent normally.
But are you saying that even in the gapped system, where the Drude weight and superfluid weight are the same, then that the Drude weight would be just the Fermi surface property?
Yes, it's a purely Fermi surface property. It's intraband.
I mean, let's say all these interband transitions that contribute to the superfluid weight are virtual. So are they? Are you sure they are not there?
Yes, I'm sure. In the Drude weight, of course. So I'm asking if there might not be this relation anymore because you're in a highly interacting system or something. But in the Drude weight, it's truly.
Okay. I see. Yes, because when I would compare my superfluid weight to the Drude weight, that would be the Drude weight of the interacting system. Then yes. Yeah. So now,
even in the interacting system, it's a Fermi surface property. If you can still define some kind of a Fermi surface.
Yeah, but maybe it has been derived by assuming the Fermi surface, and then you neglect some terms, and then if you cannot define the Fermi surface, you have to take the other terms into account, and I think that would be the case. There is a lot of literature on various things where people have just assumed the existence of the Fermi surface, and if it's large, you can basically describe everything by it.
So you're claiming that this twisted bilayer graphene is not really having a well-defined Fermi surface?
Oh, that one still has. That's not like a completely flat band system, but there the interaction is so big that it's not said that you can use all kind of formulas that have assumed a large Fermi surface, because there are these kind of other contributions. For instance, for superfluid weight, there is one contribution which comes from the Fermi surface, and then the other one that comes from quantum geometry. And now if you look at only the one that comes from Fermi surface, you might get a too small number.
Well, you have very large bands due to the renormalization. So
that actually, now the present understanding is that the renormalization makes the band big and so on. So it's more complicated question, but in principle, I'm saying that in some kind of system that has a bandwidth that is finite but small, you don't know. Maybe you should take into account these interband terms when evaluating things.
Thank you.
I had a question about the lasing. I didn't really get if I understood correctly, the lasing is from a point that has two different topological charges at the same time, like 5 and 7 or 5 and 9.
Yeah.
So how does that work? How, in kind of my very naive understanding, kind of if I go around once, I count, but how do I have two different numbers going around one point?
Yeah, so this is really the lasing emission. So, well, I usually think you maybe a lasing beam like that it goes to one direction, but these are really angles, so it goes to various angles, and depending which angle you look at, you get different polarizations. And yeah, this is maybe, I think, this lowest picture is the best. This is a theory one, but you can think that the charges are formed by having really tiny vortices next to each other.
Oh.
So then it forms like two topological charges nearby.
I see. Okay, thanks.
Thanks. I have a question on the lattice and the measurements that you were showing actually on the last slide. So you measure some very curvature, but
This? No?
No, right at the end, in the conclusions, you showed again the measurements of the, no, further in the conclusions.
Yeah.
Yes, this one.
Yes.
Exactly.
Yeah.
So the bottom plot, you're measuring some non-zero very curvature, but your system has a trivial Chern number, right?
Has a what?
A trivial Chern number.
Yes. The total Chern number is 0. Yes.
So it's just that the integral is 0.
Yeah.
Thanks.
Yeah, so these losses are not enough to create a Chern number, but at least very curvature.
A question regarding that figure. So what is the meaning of a non-Hermitian Berry phase in a lattice system or in a system like this?
Well, it's just
in which sense is not Hermitian, the Berry phase?
First of all, that its origin is non-Hermitianity. So, for instance, in our 2x2 model, if we make it to be totally Hermitian, this Berry curvature goes away. So it's like that you need this symmetry breaking from losses to have it. And then when defining it, you have to use this right or left eigenstates. There is a little bit of discussion what is the right formulation, but with one of them we got this result.
Okay. So if there are no more questions, let's thank Päivi again.